Hello, I'm Yijia from Boston University. I will introduce you to our recent work that quantifies the impact of network congestion on application performance and network metrics. This work is done in collaboration with NERSC at the Lawrence Berkeley Laboratory. To give you a brief overview of this work, we have quantified the network congestion in high-performance computing systems, and we show that network congestion's impact on application execution time is application-dependent and can be understood by MPI characteristics. And we also show that this impact is correlated with some router-level network countermetrics. In the figure on the right, we are running some experiments on the Cori HPC system located at the Lawrence Berkeley lab. And we run the mini-MD benchmark application on 64 nodes. And we show that when running with network congestion, the execution time can be several times larger than the normal cases without congestion. And the rightmost figure showing the execution time's correlation with the network metrics. And we think these knowledges will help us design some scheduling algorithms in the future to mitigate these network congestions. The motivation for this work is that people have find out that network congestion is the main cause of performance variability in HPC systems. Previous work has shown that network congestions can cause performance variability as high as 2 times, 3 times, or even 7 times. In the figure at the bottom right, these are some experiments done on the Cori system from previous work published by the co-authors of this paper. And they run some applications through multiple months with the same exactly input. And they find out the variation of this, their execution time is large, and they further decompose this execution time into compute time and MPI communication time on the left figure. And in this figure, as you can see, the MPI communication time is causing the biggest performance variation, while the compute time seldom causes this trouble. So in this work, to further quantify the impact of network congestion on different applications, we have designed the following experiments. In the figure on the right, we have the 4 different settings, and in each setting, we have the square represents 1 node in the Cori system. And the white ones represent idle nodes. The blue ones represent a parallel application taking multiple different nodes. And the gray ones are showing the network congestion. And in the setting 1, we have the continuous case, which means we run the application without congestor, but allocated in a continuous way. And the second case is that we run application, but allocate it in a spaced manner. And the third and fourth case are as the same ones, but with running the congestor together. So we are actually differentiating between 2 kinds of congestion. The setting 3 here is showing an intermediate congestion, where we have the gray nodes that are running the congestor, which creates congestion for the messages of the application that can travel through those routers. But in this case, the nodes of the congestor does not share a router with the nodes of the application. While in the fourth setting, we have the application and the congestor interleaved with each other. That means if, for example, the dashed line is showing the 4 nodes that are sharing the same router, then the application and the congestor will be creating this traffic that's congesting this node with each other. And in this work, we run the congestor using the GPCnet tool, which is a recently proposed tool by the co-authors of this paper. And we are running an RMA broadcast communication kernel throughout this study. And for the application, we are comparing 8 different applications or benchmarks. And the details of the applications are shown in this slide. we have the applications including Graph500, HACC, HPCG, LAMPS, MILC, Mini AMR, Mini MD, and QMC pack. And these applications covers a wide range of real applications running on the Correlate system. And among them, some of them are benchmarks and some of them are real applications, including LAMPS, MILC, QMC pack, and HACC. And this graph is showing one of the main results where we are comparing the normalized execution time of the applications in 4 different settings as we have mentioned. And in each cases, the same color represents the same setting, and the applications are grouped together. And so for each setting, we are running 10 different applications and taking the bar plot to represent the characteristics of these experiments. So in each bar plot, we are showing the mean maximum value and the first and the third quartiles, as well as the median black line represents the median value. And here we have several key findings from here. The first is that we show that the Graph500 and HPCG with our inputs are almost not affected by congestion. As you can see here, the median value doesn't deviate from the normal cases by 10%. On the other hand, we find these applications like HACC, LAMPS, MILC, and Mini-MD are impacted a lot by the endpoint congestion represented by the orange bar plot. And here the LAMPS is especially drawn on the right figure because it exceeds the range of the left figure. And as you can see, the LAMPS execution time of the orange case can be almost 9 times as large as the continuous case. And later I will show that after profiling using the CREPAT, it's actually these applications are having more intensive MPI operations than the other applications. And that's the reason why they are more impacted by network congestion. And by comparing the deep green bar and the orange bar, we can see that these applications are also affected by intermediate congestion shown in the deep green bar, but they are less severe than the endpoint congestion created by the represented by the orange bar. And in this figure, we are comparing the execution time with the CREPAT profiling of the applications. Especially, this table shows the profiling results of these applications, and we show their MPI operation times as these percentiles. And this MPI operation time is further decomposed into the MPI events, including the MPI all reduce, MPI send receive, bcast, test, etc. And there are also several key findings from here. First, we see that HACC, LAMPS, MILC, Mini AMR, Mini MD are high in their MPI operations. As you can see from the table, the lowest one is Mini AMR, which have 26% time in MPI operation, and the highest is Mini MD, which has more than 83% of the time spent in MPI operation. And also these applications, as you can see from the figure, they suffer from large impact from congestions. And second, we especially see that these LAMPS and Mini MR are high in their MPI collective operations. And because these MPI all reduce events are quite intensive MPI operations, and so that could be the reason why these two applications are suffered a lot from network congestion. Especially, as we can see, these LAMPS are having the most time spent in MPI all reduce. That's about 25%. So that could be the reason why this LAMPS execution time under endpoint congestion can be as high as 9 times as normal. And we also see that this HPCG and QMC pack has very low MPI operation time, and they are less than 6%. And that could be the explanation of why they are almost not affected by network congestion, as seen from this plot. And finally, we see that this Graph500 application has 31% time spent in MPI operation. But actually, it is not affected a lot by the congestion. That could be because the most of the time of MPI operation is actually spent on MPI test, as you can see from the table. It spends 21% time in MPI test. And this is a communication events that can be done independently from each other. So that could be the reason why it is not intensive MPI operation. So it could be the reason why it is not affected a lot by network congestion. And now I will show how our results can be correlated with some network metrics. This figure on the right is showing a typical Aries router in a dragonfly network, for example, in this correlate system we are experimenting with. And in this Aries router, we have 48 network tiles, and the 40 of them are tiles or called N tiles, and 8 of them are processor tiles called P tiles. And these P tiles are connecting the N tiles with node, and the N tiles are connecting the P tiles of this router and the N tiles of other routers. And Aries router counters can collect some fleet packet or stall count on each tile, and some of the counters with their full name and abbreviations are listed in this table. And on the correlate system, these counter data are managed and collected by the LDMS tool. And in this work, we will compute a stall-to-flit ratio metric following this formula. It basically is calculating calculating the stall count divided by the fleet count, averaged over all the N tiles. And this figure is showing a typical correlation with the execution time and network metrics. In these two figures, we are showing how these mini-MD's execution time is compared with the N tiles stall-to-flit ratio or with the N tiles stalls per second. And both these figures showing that there is a positive correlation between this execution time and the N tile network metrics. But on the other hand, we also see that this mini-MD execution time is negatively correlated with the p-tile stalls per second, which seems counterintuitive at the first thought. And why it is happening is actually because the p-tiles counters we collect are collecting the traffics from the n-tile to p-tiles, which is after the bottleneck of the network. So as a good analogy, if you look at the rightmost figure, if we are on a highway and there is a bottleneck in this highway, then before the bottleneck there will be high congestions, and after the bottleneck there will be almost no congestion. So if we look back into the p-tile stall per second figure, we will see that in the orange case we have large execution time. That means there are severe bottleneck, and so as a result there will be more congestion in the p-tile case but less congestion in the p-tile case. So that's the explanation of why there is a negative correlation between the mini-MD execution time and the p-tile stalls per second. So in conclusion, in this work we have shown that network congestion's impact on application execution time is application dependent and can be understood by MPI characteristics. And we also show that this impact is severer when caused by endpoint congestion than by intermediate congestion. And we also show that this impact is correlated with some router-level network counter metrics. And we think these knowledges will help us design scheduling algorithms in the future to mitigate network congestions in HPC systems. Thank you for listening.